Hello everybody, I will present our recent work on language-grounded dynamic scene graphs for mobile manipulation called MoMa-LLM. This is joint work between the University of Freiburg and Toyota Motor Europe. In our work we tackle the problem of interactive object search, which requires finding objects in unexplored environments that contain closed doors as well as target objects that are hidden within articulated objects such as drawers or cabinets. As a consequence, our embodied agent has to shape the scene to solve the task successfully. In the last year, LLMs have proven their capability of high-level reasoning. This was mostly demonstrated in tabletop scenarios or fully observed environments that lacked physical grounding of actions. The task of mobile manipulation, however, poses a new set of challenges. First of all, we face large scenes that require an efficient spatial and temporal memory. Secondly, we face unexplored dynamic environments. And third, we face a myriad of potential actions to execute. To tackle these challenges, we present MoMa-LLM that is able to take instructions in the form of natural language, ground those in dynamic scene graphs covering multiple regions in an open set manner, and provide high-level reasoning for mobile manipulation. First of all, our embodied agent is placed in an unexplored scene, and we assume access to RGBD observations and ground truth semantics. Given these observations, we dynamically construct 3D scene graphs, including a navigational Voronoi graph covering the distinct regions and objects of the explored scene. Different to previous work, we separate regions based on scene doors. Lastly, we classify each region in an open set manner based on the contained objects. Next, we provide a structured knowledge representation of the obtained scene graph to our high-level LLM policy. This involves a general specification of the task, such as find a stove. Then, we interleave the scene representation with a set of high-level actions available to the agent, which includes navigating, opening and closing an object, exploring unseen regions, and calling done whenever the task is deemed to be completed. Second, we provide a list of regions and contained objects extracted from the scene graph, which also includes unexplored areas within these regions. In order to form temporal memory, we list the last executed actions, which allows for autonomous long horizon execution. Finally, we ask the LLM to select the high-level action and the involved scene entities. To introduce interpretability, we also ask the LLM to reason about its own actions. And throughout our experiments, we found that this more natural task and scene description improves task success over feeding JSON-formatted scene graph data in a brute force manner. Based on the high-level action types, we equip MoMa-LLM with a set of low-level downstream policies. For pure navigation, we utilize a classical A-star planner. In case of articulated object manipulation, we make use of previous work, namely N2M2, that equips a mobile manipulator with zero-shot navigation and manipulation skills. Lastly, we use frontier-based exploration when asked to explore novel areas. In simulation using iGibson, we find that MoMa-LLM outperforms both zero-shot and trained baselines in overall task success given reasonable time budgets. As part of our work, we also introduced the novel ORG-E metric, which represents the area under the efficiency curve. The ORG-E metric alleviates the need for arbitrarily set maximum time budgets of the success rate. All in all, we obtained the highest success rate SPL as well as ORG-E, while minimizing the number of object interactions and distance traveled compared with previous zero-shot and trained baselines. We also demonstrate the capabilities of MoMa-LLM using a Toyota HSR mobile manipulator in a multi-room scene in the real world containing closed doors and various cabinet and drawer types. As a result, we observed that MoMa-LLM shows significantly reduced travel distance and fewer articulated object interactions. Lastly, we demonstrate that MoMa-LLM scales zero-shot to more complex queries such as I am hungry, find me something for breakfast, as you can see here. So we'll start with the HSR being placed in the living room of our scene, and MoMa-LLM picks the first high-level action, which is go to the door within the living room, open it to explore novel areas. Our robot does that and enters the kitchen. On the kitchen counter, you can already observe cereals and coffee, and the high-level policy picks the next action, which is opening the closed fridge to reveal more objects that are potentially relevant to making a breakfast. Our N2empty policies generate these actions, and as you can see, we found milk, and our high-level LLM policy deems that the task is completed because we found coffee, cereals, and milk. As part of this work, we make the task definition and code publicly available, so feel free to check it out on GitHub. Thank you very much for your attention.